Hello! In this video, I'd like to make a comparison between two of the logics that I've introduced involving words. Specifically, the weak monadic second-order theory of two successors, which I introduced earlier in this series, and the word logic, which I introduced in my regular languages and model theory series. Both of these logics involve words and are equivalent to various types of automata, but they wind up being very different in terms of what they can express. So the objects of weak S2S are words on the alphabet L and R, and we like to use that particular alphabet as a mnemonic reminding us how this corresponds with finite state tree automata. Specifically, words on these two characters correspond to locations within a binary tree. So for instance, if we have, let's say we had, here's the root and we want to talk about this particular point here, then the question is, how do you get to this point from the root in terms of going either to the left or to the right? Well, to get here, you first need to go to the left, and then you need to go to the left again, and then you need to go to the right. And so this node here corresponds to the word LLR. And so just like how in weak S1S we were talking about positions in a word are indexed by the first order elements of weak S1S, that is natural numbers, right? Positions in a word are indexed by natural numbers. Positions in a tree word are indexed by the first order objects in weak S2S. So specifically, words on the characters L and R. And then of course, we don't just have words. This being the weak monadic second order theory, we have finite, that's the weak part, and then monadic second order tells us that we're talking about sets of first order elements as well. So in weak S2S, we have two types of variables, one type for talking about words, I'll use lowercase letters for that, and one type for talking about finite sets of words, I use uppercase letters for that. On the other hand, in the word logic, we can only talk about words. We can't talk about sets of words. But these logics do have a lot in common. In weak S2S, as primitive, we have the successor L and successor R operations on words, the tack an L onto the end of a word and tack an R onto the end of a word operations. And over in the word logic, we also have similar successor operations. In weak S2S, you can show this is not a primitive, but it's fairly easy to talk about. You can talk about the prefix relation, right? We say that one word is a prefix of another if it's an initial segment of the other word. And in the word logic, this is actually a primitive. So far, it seems like weak S2S is winning in terms of expressiveness. The word logic can't talk about sets, and weak S2S can talk about all of these things here and finite sets of words. However, it's not quite that simple. The last primitive in the word logic is the equal length relation, which just tells you if two words have the same length. But weak S2S, it turns out, actually can't express the equal length relation. And this is actually fairly simple to show, taking advantage of our correspondence with finite state tree automata. Suppose that we had some formula phi in weak S2S that was true if and only if x was the same length as y. Then we could turn this formula into a corresponding automaton, a sub phi, and it would have to accept some sort of encoding of the pair RRRR LLLL. And in particular, the encoding of this pair looks like this. We're going to have some sort of tree word where each node is labeled with a pair from the alphabet AB, and then there's also a bottom character. And to indicate that the first input is RRRR, we're going to want to have a b in the first coordinate at position r, 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 r. And then to encode the fact that the second word in the tuple is L, 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 we're going to want a b in the second coordinate at position L, 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 L. And then we just fill with a's above b's and bottom characters where we don't need it. And so a sub v would have to accept this tree here. But it couldn't accept this tree here, right? This encodes if this were 5 r's and 4 l's. And so somehow, as this automaton worked its way up these two branches, it would have to keep track of the lengths of each of the branches so that it could do the comparison at the root. And what that means is that a sub v needs to keep track of arbitrarily large numbers, which requires unbounded memory. And so hopefully that gives you an intuition as to why such an a sub v can't exist. There can't be a formula phi in weak S2S that recognizes equal length words. There's another argument that weak S2S can't express the equal length relation, which is that if you add the equal length relation into weak S2S, you can show that the language suddenly becomes undecidable, suddenly becomes Turing complete. And so instead of one of these languages being strictly more expressive than the other, they wind up being incompatibly expressive. This one being able to express equal length and some other things, and this one being able to express sets of words. And so naturally you might ask the question, are sets of words the only thing that weak S2S can express that the word logic can't express? In other words, we're interested in the question, what sorts of things can weak S2S say about individual words? In the hope that maybe we'll be able to find something that weak S2S can say about words that the word logic can't. And it turns out that the answer is no. Anything that weak S2S can say about words, the word logic can also say about words. So really the only thing that we gain by going to weak S2S in terms of expressiveness is that we can talk about finite sets of words. This is very similar to the situation when I compared weak S1S with Büchi Arithmetic. These are both logics involving natural numbers, and they have a very similar incompatibility of expressiveness going on. Right? Weak S1S allows us to talk about natural numbers and finite sets of natural numbers, whereas Büchi Arithmetic only allows us to talk about natural numbers. Weak S1S has, of course, the successor operation, the +1 operation, as a primitive. In Büchi Arithmetic, it's not a primitive, but it's very easy to talk about the +1 operation. On the other hand, just like how the word logic has this extra feature that it can talk about, Büchi Arithmetic has actually two extra features it can talk about. Büchi Arithmetic can talk about addition, and it can talk about the V2 operation, the give us the highest power of 2 dividing another number operation. And weak S1S specifically can't talk about these two things. And again, there's two ways to show this. The first is very simply adding these on to weak S1S and showing that the result is Turing complete. I'm not actually sure if that's true for V2. I know that's true for addition. I'll have to check for V2. And then also in the previous video where I compared these, I actually worked out exactly what weak S1S could say about natural numbers. And it essentially amounted to Boolean combinations of assertions that the difference between two numbers fell into some eventually periodic set of natural numbers. Or maybe a specific number fell into some eventually periodic set of natural numbers. And notably, this is stuff that Büchi Arithmetic can talk about just using addition. And so in some sense, the only thing that weak S1S can talk about that Büchi Arithmetic can't talk about is finite sets of natural numbers. If we're just talking about natural numbers, any predicate that we can talk about in weak S1S Büchi Arithmetic can also talk about, but definitely not vice versa. Weak S1S can't talk about addition, can't talk about V2. And again, one way to show that is to show that when we relationalize these, they aren't of this form. So let's do this. Let's try to analyze what sorts of things weak S2S can say just about words, not about finite sets of words. Right? If we're restricting to just predicates that take in first order variables, what sorts of things can weak S2S talk about? And we can show that those things the word logic can also talk about. And this sort of analysis will be very similar to our analysis of the first order predicates in weak S1S. Let's start, for instance, with just predicates that take in a single input. Right, so suppose that we have some sort of predicate phi, takes in one word as input, and it's written in the language of weak S2S. It's, of course, allowed to have these second order capital letter variables inside of it, but it's only allowed to have lowercase x as a free variable. It's saying something about the word x. What sorts of things can we say about a particular word? Well, using our fundamental theorem, we can translate phi into a corresponding tree automaton. And this tree automaton is only going to accept encodings of singletons. What's that going to look like? What happens if we have a word and we want to translate it via the correspondence between weak S2S and tree automata? Well, it's going to look something like this. It's just going to be a single path. Along that path, we have the characters A up until we reach the end of the path where we have a B. And in particular, this path here encodes the word. Let's see. So we go to the left, and then we go to the right, and then we go to the left again. So L, R, L, and then we go to the right twice, R, R. Right, so this is how we encode this particular word as a tree. And the idea is that our automaton, A sub phi, is only going to accept tree words of this form, and it's only going to accept tree words of this form that correspond to words that satisfy phi. And that'll be exactly the tree words that it accepts. And if you think about it for a little while, this is actually kind of weird. When we run a word through an automaton, we're working from left to right. Right? We read this character first and we read this character last. However, this character here corresponds to this direction, this branching direction up here. And this character here corresponds to the fact that we branched to the right down here. And so the start of this word corresponds to the root, the direction we went at the root, and the end of the word corresponds to the direction that we went leading up to the leaf. Well, if you think about it, tree automata typically work from the leaves to the root. So it's a little bit backwards, and we just kind of have to deal with this backwardsness. Just like what we did when we were analyzing weak S1S, we're going to want to take all of the states and transitions of this automaton that have no futures, that can't be part of an accepting word, and get rid of them, so that we're just looking at the important part of our particular automaton A sub phi. And that's going to be a lot of them, right? The only types of tree words that get accepted by this particular automaton look like this. They're a path of A's ending in a B. So in particular, there's no branching. And that's very convenient. All that we're left with are transitions that look like some sort of specification for the state as we're working our way up this tree, the state that we want to put at the leaf. The only character that we could expect to see at a leaf is a B, and that winds up giving us some state here when we run it through our transition function, and that'll be kind of the start state of this whole thing. If we read a character A, it has to be the case that one of the two children, exactly one of the two children, has a state associated to it, and the other one just isn't there. So if there's a left child, if we have a node labeled A that has just a left child, that's going to have some state associated to it. So what state do we associate to the parent? So we're going to have transitions that look like this for some states Qi and Qj. And we're also going to have transitions that look like this. Nodes labeled A that don't have a left child but do have a right child that gets some state associated to it. What state do we associate to that node? And this is it. These are the only types of transitions that A sub phi could possibly have when we get rid of all of the transitions that can't show up in accepted words, the transitions we don't care about. So let's actually look at a specific example of a possible A sub phi. Let's say the set of states is just 0 and 1. And let's say that when we read a B at a leaf, we associate state 0 to it. If we have a node labeled A that has a left child with state 0 and no right child, we give it state 1. If we have a node labeled A that has a left child in state 1 and no right child, we give it state 0. If we have a node labeled A that has no left child and the right child gets state 0, let's give it state 1. And actually, if the right child has state 1, we'll also give it state 1. And let's imagine running this automaton on this particular tree word here. We're going to associate state 0 to this node here. This A has a right child with state 0, so we associate state 1 to it. This A has a right child with state 1, so we associate a state 1 to it. This A has a left child with state 1, so we associate state 0 to it. And we work our way up, and it turns out that we associate state 0 to the root. And let's say that the set of final states actually is the state 0. So this tree word actually is accepted. Now, if you think about it, what we've done here is we've worked our way up the tree, and instead of reading characters, right, we read A's all the way up the tree. We're actually reading whether or not there's a left child or a right child. Right, we started out in state 0, and then when working out the state of this node, we saw the fact that it has a right child instead of a left child. So we were kind of reading an R, and that took us into state 1 when we looked it up on our transition function. And again, we went from 1, we were kind of reading an R, took us to state 1. If we're in state 1, we're kind of reading an L, because this node is a left child. This branch is going in the left direction. That took us to state 0. And we're kind of working our way up this word, transitioning states. And we can actually formalize this in some sense. We can translate this tree automaton actually into a word automaton that works its way up this word and spits out the states that we would get along this path, right? So this tells us that this automaton should start out in state 0. This tells us that if we're at a node and we have a child to the left with state 1, so this node here has a child to the left that we gave state 1, then this node should get state 0. Right? That's kind of what this value of the transition function is telling us. And we translate all of these into corresponding values of the transition functions, right? This tells us if we have a node that only has a right child that gets state 0, then our node gets state 1. And of course, we're looking for it to be the case that when we're done reading our word, we wind up in an accept state. And it helps to kind of draw in the run when we're reading this word. We start out in state 0, go to state 1, 0, 1. Our final state is state 0. And so the fact that phi was true of LR, LR, corresponded to the fact that A sub phi accepts this particular tree here, this particular tree word, which corresponds to the fact that this automaton, let's just call it A, accepts this word, RRL, RL, right? We're reading it this way. So phi is true of a particular word if and only if this automaton here accepts its reversal, if and only if the reverse of that word is in some regular language. Well, it turns out that the regular languages on words are closed under reversal. If we have a regular language, there's various ways of seeing this, but if you reverse all of the words in that language, the resulting language is also regular. And so that means that phi holds exactly of words that fall into some regular language. So the predicates that we can express in weak S2S are exactly the regular predicates, exactly the regular languages. And if we compare this to the word logic, well, the word logic can also express some word X belonging to an arbitrary regular language. Those are in fact exactly the things we can express in a single variable in the word logic. It's worth taking a moment to compare our situation with the situation that we had when we analyzed these sorts of predicates in weak S1S. In weak S1S, all of our predicates of one first-order element looked like X belongs to some eventually periodic set. And of course, the eventually periodic sets are kind of the one successor analog of a regular language. They're the sets of lengths of words on an alphabet with one character in it. What about if we have some sort of predicate in weak S2S that takes in two first-order elements, two words on L's and R's? Well, when we try to encode a pair of words as a tree word, it's going to look something like this. We're going to have one branch from the root that's going to lead, the path of that branch is going to be the word X, right? X is L's and R's, so that's going to be the path of this branch here. And then we're going to have some other branch, and maybe this branch is off of this branch, following the directions in the word Y, right? Again, Y is a sequence of L's and R's. It's going to direct us from the root to this point here. And this bit here corresponds to whatever common initial segment X and Y have. And it's at this point where they branch apart. Of course, maybe they don't have anything in common, in which case they branch at the root. This is kind of the general case. And then, just like we did way back with ordinary word automata, we want to associate to every position in this thing a pair of either an A, a B, or an end of word character, which I'm using the bottom symbol for. This node here, let's say it corresponds to X, we'll have a B in the first coordinate and a bottom in the second coordinate. Along this branch we'll have A's followed by bottom characters. This point here, let's say it corresponds to Y, we'll have a B in the second coordinate and a bottom in the first coordinate. All of the nodes along this branch will be of the form bottom A, and this node and everything above it will get an A, all the way up to the root. So this is kind of generally what the tree representing X, Y will look like, although of course, again, it might be the case that X and Y have nothing in common, have no common prefix. And it could also be the case that these branches here are of trivial length, right? It could be the case that X is an initial segment of Y, or Y is an initial segment of X, or maybe X and Y branch, but they branch in the opposite order, with Y going to the left and X going to the right when they first branch. So there's lots of possibilities. Here are some possible concrete trees that might be encoding pairs x, y. This one encodes the pair, both of the b's are located at LLR. For this tree, the first b is located at LLR and the second b is located at L. For this tree here, the first b is located at L and then the second b is located at LLR. For this tree here, the first b is located at LLR, and the second b is located at LR. And this tree here is just the reverse of that. The first b is located at LR, and the second b is located at LLR. So just like when we were analyzing weak S1S, we're going to be able to divide up the pairs x, y into lots of different templates that they might fall into. One template for if x is equal to y, one template for if y is a prefix of x, one template for if x is a prefix of y, and so on and so forth. And this is just a sampling of some of the templates that we're going to have. It's going to be convenient to break up our analysis. We have our phi, we can turn it into some a sub phi, and we're going to want to take the language of tree words accepted by a sub phi and intersect it with various templates of shapes that these tree words could have. And each of these cases corresponds to a tree regular language. You can find some sort of tree automaton that detects when all of the characters in a tree word are AAs or BBs. You can build a tree automaton that detects when there's one branching, it's not at the root, it's AAs all the way up to that branching, and then it branches off into something that looks like bottom A's and bottom B's. And then another branch that looks like A bottoms and B bottoms, and the first branch branches off to the left and the second branch branches off to the right. Now again, just like our analysis with weak S1S, this first shape where x is equal to y is the easiest one to analyze. We're just looking at languages of tree words that contain only tree words of the form some branch, it's AAs along that branch, and BBs at the end of the branch. Well, this is exactly the problem that we already solved, except we've replaced the character A with the character AA and the character B with the character BB. And that's kind of what we expect, right? If we're building an automaton for the predicate a sub phi of xy, and x is equal to y, we're really just building an automaton for the predicate phi of x. I now want to skip ahead to this case here, which I think handles all of the interesting things, and you can just kind of generalize the analysis to all of the different cases. Right, so we're considering the case we've taken the language of our automaton, we've intersected with the language where x and y diverge after the root, so they have a non-trivial greatest common prefix, with x going to the left, so that prefix with an L tacked onto the end is a prefix of x, and that common prefix with an R tacked onto the end is a prefix of y. So our encoding, it might specifically look something like this, and in general, it's going to look something like this. When we were analyzing predicates on two or more variables in weak S1S, we found it useful to draw out a transition diagram. It's going to be a little bit tricky. It's always kind of gross to try to draw out the transition diagram for a tree automaton, but we're still going to want to do something similar. We're going to want to divide up our states into different groups, and that's what we were doing with our transition diagrams in the weak S1S case. Specifically, I'm going to want to divide up the states of our automaton into states that can show up along this branch, states that can show up along this branch, and states that can show up at the merge or further. I'll call these states Q1, I'll call these states Q2, and I'll call these states Q3. And once we've gotten rid of the states and transitions of our automaton, our intersected automaton that have no futures, this is actually going to form a partition of the remaining states. If we had a state that could show up both along this branch and along this branch up here, we could take the entire piece of the tree between those two states and either cut it out or insert multiple copies of it, and it would give us a completely different shaped tree, a tree that wouldn't encode a pair at all. And it would still satisfy the transition relation of the original automaton. This is kind of like our pumping lemma that we talked about. So now that we have this partition of our states, we can analyze the transitions within and between these different groups of states. Again, we did this visually in the weak S1S case, but I just want to write the transitions out for the tree automaton case. So once we get rid of all of the states and all of the transitions that have no futures, that can't show up in a run of our specific automaton on a word in this specific language, we're still left with quite a lot of possible transitions. And this is all of them. So our transition function is going to tell us if we're at a leaf and we see a B bottom, then we need some sort of start state for this leaf here. And that start state is specifically, it's going to be some Q0, and it's specifically going to be in Q1. It's going to be in this set of states for this branch here. So I'm using a superscript 1 to indicate that this state is in Q1. The transition function also tells us if we're at a leaf and we see a bottom B, give us some state. There's going to be some specific start state in Q2 for this node here. Our transition function is going to tell us that if we're at a node and we see an A bottom character, we're going to be somewhere along this branch. And so it's necessarily going to be the case that our child node has a state in Q1. Let's call it Qi. Again, I'm using this superscript 1 to indicate that it belongs to Q1. And of course, because this is a path, there isn't going to be a child in the other direction. There's no branching. And then the transition function will tell us for various Qi's in Q1 what state to assign to this node here. It's going to be some Qj, and that's also going to be a state in Q1. And the reverse, if we're at a node that has an A bottom character at it, it might have no left child and a right child. And so if the right child gets state Qi, which is going to be in Q1, we need to assign some sort of state Qj, which is also going to be in Q1, to our node with the A bottom character. And then similarly, the reverse. If we're at a node that has the character bottom A associated to it, we're somewhere along this branch. So again, we expect to see only one child, and depending on whether that child is a left child or a right child, and what state is at that child, we expect there to only be states in Q2 associated to that child. We're going to assign some state Qj to our node, and again, that's going to be a state in Q2. And now kind of the really interesting bit are the transitions that look like this, where we have a node that has two children. This node has to have the character AA associated to it. It's going to be our branching point. The node to the left is going to get some state in Q1 associated to it, let's say Qi. The node to the right is going to get some state in Q2 associated to it, let's say Qj. And again, based on what states get associated to the two children node of the branch point, we're going to associate some state Qk to the branch point itself. And that Qk is going to be in Q3. It's going to be in the set of states for this bit of the tree here. And then finally, as we work our way up this branch, we're going to see nodes that have the character AA associated to it. This is a branch, so we're only going to see one child node, either a left child or a right child. It's going to have state associated to it, some state in Q3, so I'm using QI3 for that. And depending on which state gets associated to that child, and whether it's a left child or a right child, the transition function will tell us some state in Q3 to associate to that node. And then we'll work our way all the way up until we get to the root, and then determine whether or not it's accepting or not. The only accept states are going to be states in Q3. It can't be the case that we have an accept state that's reachable in Q1 or Q2, or we might be able to stop our trees somewhere around here or somewhere around here, and so they wouldn't have the shape that we wanted them to have, and they wouldn't describe pairs in weak S2S. So now that we have this breakdown of our automaton, let's focus on the set of all transitions that look like this. And again, these have to be transitions that look like this that have futures. So if we focus on transitions that look like this, each tree word in our language is going to have exactly one such transition in it. The transition that shows up when our two branches merge together. And so let's partition the set of tree words in our restricted language by which of these transitions shows up in it. I'll show you what each class in that partition has to look like in just a moment, but understand that because there's only finitely many transitions that look like this, our resulting language is going to be a finite union of whatever each of those classes of this partition wind up looking like. So let's say we have a particular transition in mind, and we know that our word has that transition at the branch point. What does that mean our word's going to look like? Let's look at just this bit of the tree word. Again, in terms of symbols, this bit is kind of boring, right? It's all AAs. But the interesting question is what sorts of branchings can show up here? What sorts of combinations of L's and R's? And just like we saw when we analyzed the first case, this pair of transitions here acts like an automaton that's reading not characters, but whether or not the branching goes left or right. It's reading the L's and R's of our words, X and Y, or rather, so this bit is the common prefix of X and Y. So it's reading the L's and R's of the common prefix of X and Y, and using that to transition from states to states. And just like before, this automaton is reading this common prefix backwards, but that's okay. The reversal of a regular language is still regular. So there's some sort of regular language, the regular language given by this automaton when we translate it. Let's call it L3, such that this common prefix has to fall into L3. Oh, I guess I should note, QK is kind of acting like the start state for this automaton. And of course, the final state is the same as the final state for the whole automaton. For this branch here, leading from the start state where the B bottom character appears, leading all the way up to this QI node, this bit here also is given by some sort of regular language, right? The branchings left or right fall into some regular language. And again, that comes out of translating these two transitions. Again, the characters that we see are quite boring. We're always going to see A bottoms as we go along this path. But whether or not we branch left or right, the corresponding character, this bit here, so it's the bit, so we have the common prefix, and then we have an L, and then whatever X does beyond that is this bit here. And it's going to fall into some regular language, and we can figure out exactly what that regular language is by interpreting this as a finite state automaton that's reading the sequence of L's and R's backwards. So I'm going to call that regular language L1. Oh, and I guess, again, I should clarify about the start states and the finish states. The start state of this automaton should be this start state here, and the final state should only be Qi. And then again, we have exactly the same situation here. Along this branch, the sequence of L's and R's in this last bit of Y, right? We have the common prefix, we have an R, and then we have this last bit of Y. And that sequence of L's and R's has to also fall into a regular language. Let's call it L2. And so ultimately what this is going to look like is X is going to be some element of L3, followed by an L, followed by some element of L1, and Y is going to be that element of L3, followed by an R, followed by an element of L2. So the set of all pairs x and y whose encodings as tree words are accepted by this automaton here, that is, the set of all pairs x and y that satisfy this, that also satisfy phi, is going to be some finite union of sets of this form. And so all it seems like weak S2S is allowing us to say when we have two words, x and y, is we can kind of compare them up to a point, but only compare them up to the point where the words start differing from each other, only up to the greatest common prefix, and then they split apart and we can only talk about the remaining bits falling into various separate regular languages. Now that's not quite the case, because remember we're looking at finite unions of things of this form. And so it could be the case that somehow something about W3 affects what W1s and W2s are allowed, but we're much more restricted than we would be in the word logic, where predicates of this form are translated into automata that kind of read in the pairing of these two words. And so they can do very fancy things, like check to see if one word is another word shifted over one unit. You can't do that here. And of course, we have to look at the other templates. What happens if we're just restricting our attention to cases where x is a prefix of y? Our tree words representing these sorts of things are going to look like single branches where it's AAs for a while, followed by a BA. This BA is located at location X. And then a continuing branch given by the bit of y after x, right? X is a prefix of y, so y has something added on, and the L's and R's that make up this branch are that bit that's added on. And this branch consists of bottom A characters and ends with a bottom B character. But the analysis of these sorts of things is going to be very similar to the analysis of these sorts of things. Right? We look at what sorts of transitions can show up in kind of the key point here. We divide up our states into, in this case, just two parts. The states that can appear here, let's call those Q2, and the states that can appear here, let's call those Q1. And then the transitions that we see here have to look something like our node has character BA. It has either a left or a right child, but not both. That child has a state in Q1, and of course the result is a state. This node here gets a state in Q2. And again, this bit of the tree, whether it's L's or R's, is going to form some regular language. This bit of the tree, whether it's L's or R's, is going to form some regular language. And so we take the union over these possibilities over all possible branches that look like this. So when we're unioning over these possible transitions and we're looking at one of these transitions, we're looking at a language that looks like X is some word W2 in some regular language L2, and Y is that same W2, right? X is a prefix of Y, We were restricting our attention to that. Followed by an L, followed by some word in some other regular language, L1. And of course, if we were looking at a transition that looked like this, when we're doing the union over everything, this L gets replaced by an R. And so in the end, we can describe the language accepted by just A sub phi with no restrictions, or the set of all pairs xy satisfying phi as a union over all the different possible templates of the union over all possible kind of key transitions of really basic languages that look something like this. And that's kind of gross, but we can do a lot of cleanup, right? We could move this L into the W1. When we simplify everything down, we'll be able to write phi of xy as some finite disjunction, finite OR, of predicates of the form there exists a W1 in some regular language L1 through W3 in some regular language L3, such that x is W3, W1, and y is W3, W2. Right, the special cases that we got out of our templates are actually coming from, well, if L1 is just the language containing the empty word, then this looks like this. X is a prefix of y. And if L1 and L2 are both languages just containing the empty word, then we're looking at a situation like this, where x is equal to y. So we fully classified the predicates in weak S2S that take in 2 first-order elements. What happens if we have even more first-order elements? What happens if we want to analyze the predicates that take in 3 first-order inputs in weak S2S? Well, we'll have to do exactly the same sort of analysis. We'll have, in this case, the number of different types of templates is growing combinatorially. But a generic template might look something like this. We're now assigning triples of characters to each node because, well, we're trying to encode a triple. There'll be a b in the first coordinate at position given by the first element of the triple. There'll be a b in the second coordinate at position given by the second element of the triple. And there'll be a b in the third coordinate given by the third element of the triple. Just like before, we're going to want to look at an automaton that accepts tree words that represent tuples x, y, z that satisfy phi that also have this particular form. And remove from that automaton all of the states and transitions that don't have a future. And once we do this, just like before, we'll be able to partition the states of this automaton, this time into 5 different groups. And again, the key thing is to look at the state transitions for this node here and this node here. Once we fix the states that the nodes around here wind up getting and the states that the nodes around here wind up getting, all of these branches wind up turning into ordinary finite state automata, just like they did before, right? We have some sort of end state, we have some sort of start state, there's going to be a unique state that we have to assign to this node, and then our automaton, it's reading, the characters that it's reading are boring, right? They're all A bottom bottoms along this branch, but the interesting thing is whether or not the branch goes left or right, and it's going to be reading that. It's going to read that, run it through kind of a finite automaton process, and again, once we've determined the states over here, there's kind of a determined endpoint for this automaton. There's a determined end state for this automaton, and so the possible paths that we could see here form some sort of regular language. In this case, I'll call that regular language L1. Same thing here, we'll have another regular language L2, same thing here, another regular language L3. Once we've determined the states around here and around here, we'll have a start state and a final state determined for this automaton here. So the set of L's and R's making up this branch will also fall into a regular language, let's call it L4, and the set of possible branches, the set of possible L's and R's for this bit are also going to fall into a regular language, call it L5. When we clean this up at the end, it's going to look something like there are some W1 through W5 falling into regular languages, L1 through L5, such that X is W5 concatenated with W4, concatenated with W1. Y is that W5 concatenated with that W4, concatenated with some W2. And Z is that W5 concatenated with W3. We'll get one of these, we'll get a 5 tuple of regular languages for all possible assignments of states around this node and around this node, for all possible pairs of transitions that could happen here and that could happen here. And then we just have to take the union of a bunch of these, the union over all possible pairs of transitions, one that could happen here and one that could happen here. And then finally, we take the union over all possible templates. And different templates might give us slightly different versions of this. It might be the case that Y and Z have the larger common prefix, as opposed to, in this case, where X and Y had the larger common prefix. But ultimately, our language, the set of tuples x, y, z satisfying our predicate phi is going to be some finite union, some finite OR of things that look kind of like this. Another way we could look at these breakdowns of our predicates is something like this, right? What we're saying here is that the common prefix of x and y, the greatest common prefix of x and y, falls into some regular language L3. And the remainder, x minus the common prefix, so our W1, is going to fall into another regular language. This will be kind of a partially defined notion of subtraction that takes in something like W3, W1, and when we subtract off W3, we're left with W1. And if you input things that aren't valid, it doesn't give you anything. It's undefined. And Y minus the common prefix falls into another regular language, L2. And so we're able to write this predicate phi here as a finite disjunction, a finite OR of ands of things involving the greatest common prefix and x and y, and assertions that things fall into various regular languages, and also assertions that the difference between two things falls into a regular language. And this looks a lot like our classification for weak S1S, right? We were able to assert that various x fell into some eventually periodic set. Well, the analog of that is that some x falls into some regular language. Or we could say that the difference of two elements in weak S1S fell into some eventually periodic set. Again, this is kind of the analog of that. Except that now when we went from weak S1S to weak S2S, suddenly the greatest common prefix has gotten involved. But this classification here doesn't just work if we have two variables. It also works in the three variable case, right? We could take something like this and rewrite it as, right, assertions that the greatest common prefix of x, y, and z, it's going to be W5, falls into some regular language, and assertions that the difference between the greatest common prefix of x and y and the greatest common prefix of x, y, and z falls into some regular language. That's going to be our W4, so it's going to fall into L4. Right, the greatest common prefix of x and y is W5, W4, so we're subtracting off W5, we'll be left with W4. And then we can write our W1, W2, and W3 like this, and we just assert that each of those is in the appropriate regular language. So we and all of these together, that's going to describe one of these things, and then of course we have to again take the disjunction, the or over a bunch of things that look like this. So ultimately, every predicate phi of first order variables in weak S2S can be written as some sort of Boolean combination, and we're not even using not here. It's just a combination of ands and ors of atomic formulas involving the greatest common prefix operation, assertions that various elements, either greatest common prefixes or individual inputs, fall into some regular language, and assertions that the difference, where we're very careful about how we define this, that the difference between two things that we can write out falls into some regular language. And this is exact. Every predicate can be written this way, and anything that can be written this way can be written in weak S2S. That's a little bit tricky to see. It's not that bad to show that we can talk about greatest common prefixes in weak S2S. After all, we can talk about prefixes in weak S2S, and it's certainly possible to assert that a particular element of weak S2S falls into some regular language. And this one's a little bit tricky, showing that the difference, we can't talk about the difference operation in weak S2S. We can't take an x and a z and talk about x minus z, but we can say that the difference between two words falls into a regular set. And that we actually get out of the analysis that we did when we were looking at templates of x and y, where y was a prefix of x. So that's our complete classification. We get some really interesting closure properties. We know, for instance, that the collection of things we can write like this as in terms of ands and ors of expressions like this has to be closed under negation, because this is equivalent to weak S2S, and weak S2S is closed under negation. And it also has to be closed under quantifiers for all x and there exists an x, because weak S2S is closed under those quantifiers, and again, they're equivalent. So that's kind of neat. I wonder if anything happens out of that. And importantly, you can show that all of these things are things that the word logic can talk about. So again, just like when we were comparing weak S1S with Büchi Arithmetic, we see that anything that doesn't involve finite sets of words that weak S2S can talk about, the word logic can talk about. The only thing that weak S2S can talk about that the word logic can't is finite sets of words. So thanks for watching. Let me know if you have any questions in the comments section below, or let me know what you learned from this video. And be kind to each other.